Hello friends, welcome back to my YouTube channel. This is 8th part of my discussion on leaching, and I will continue my discussion on stage-wise leaching. And the topic for today's discussion is multi-stage counter current leaching. So at the end of today's discussion, you will know how to write material balances for various material balances for multi-stage counter current leaching, then how to follow those material balances on the equilibrium diagram, and you will also learn how to find out the required number of equilibrium stages to bring about the desired separation. So let us begin the discussion. To start with, we will know little bit about the stage-wise contact. So for that, I am going to consider a simple ternary system. In this case, feed is a mixture of solids B and C. It is a mixture of two solids B and C. Out of this, C is the solute that is to be separated by leaching, whereas the other solid, that is B is the insoluble solid, and it is called the carrier solid. So C is present in the mixture with B, and the task is to recover C by using stage-wise leaching operation, and in this case by using multi-stage counter current leaching operation. So we are going to understand this multi-stage counter current leaching. The solvent used in this case is A. So the components involved are A, the solvent that is used for leaching, then B, the insoluble solid, which is the carrier solid, and C, which is the solute to be separated by leaching. The feed mixture, that is B and C, B plus C, and then solvent A, they are contacted in a stage-wise manner. So in this operation, in stage-wise contact, the feed mixture and the solvent, they are contacted in a stage-wise manner. And for simplification, in order to simplify the analysis that is involved, you can make few assumptions. Which are these assumptions? You can assume that solid B is not soluble in solvent A. Only the solute C is soluble in solvent A. So solid B is not at all soluble in the solvent. This is one assumption. Then you can assume that there is no preferential adsorption of either solute C or solvent A on the surface of solid B. So I have discussed this in all my videos on stage-wise leaching, but still I'll just tell you briefly. So in this case, you have a mixture of two solids B and C. This is the solid mixture B plus C, and you are contacting it with a solvent. The solvent in this case is A. So what happens after sufficient time? What happens? C from the solid mixture, it enters into the solvent, and there is formation of solution of C in A. And when you have solution of C and A, when you have solution of C in A, then we will assume that neither A adsorbs preferentially on the surface of the solid, nor C adsorbs preferentially on the surface of the solid. That is, in simple words, we are ignoring the adsorption of either of the two components. So there is no adsorption of any component from the liquid solution. And in the liquid solution, you have two components, solvent A and solute C. So no preferential adsorption of either solute C or solvent A on the surface of the solid B. This is the second assumption. And the third assumption is the quantity of solvent A is enough to dissolve all solute C in it. The quantity of solvent that you use in the operation, it is enough to dissolve all solute C that is present in the solid mixture. So this assumption is required in order to allow an equilibrium to establish between the liquid phase and the solid phase. So for that, there should be sufficient amount of solvent. The quantity should be sufficient to dissolve all solute C that is present in the solid mixture. So this is the third assumption you can make in order to simplify the analysis. So for simplification, you can make these assumptions. Solid B is not at all soluble in solvent A. No preferential adsorption of either solute C or solvent A on the surface of solid B. And the third one is the quantity of solvent A is enough to dissolve all solute C in it. So with this assumption, you can simplify the analysis. Now each stage, when you have stage-wise contact, which will be carried out in a stage-wise equipment, and in that, each stage should have the following provisions in order to have successful leaching. So each stage should have the following provisions. First, there should be a provision for mixing the solid mixture, solid feed mixture, that is B plus C and solvent A. So there should be a mixer in the stage which will mix the solid feed mixture with the solvent, and there should be provision either for settling, filtration or drainage of the resulting slurry of insoluble solid B immersed in the solution of solute C in solvent A. So when the solid feed mixture is mixed with the solid solvent A, what will happen? There will be formation of a slurry. And in order to separate the clear solution, we need to allow the slurry to settle, or you can filter the slurry, or you can drain the clear solution from the slurry. So the point is, there should be either provision for settling or filtration or drainage. So there should be a provision for mixing and provision for either settling, filtration or drainage of the resulting slurry. So each stage in the stage-wise contact equipment should have these two provisions. So you can understand this with the help of this schematic diagram. So you have a stage and you are admitting the feed solid mixture, that is B plus C, into the stage, and then you are also admitting solvent A in it. So initially there will be a mixer which will mix the two phases, and then the resulting slurry will then be transferred to a settler which will settle the solids, and then you can remove the clear solution. So in this case, I have shown a combination of mixer and settler which forms one stage in the operation. Then after settling, the clear solution is removed as overflow, or you can call it as clear solution. So it is solution of C in A, that is A plus C. And then the settled solids, you can remove them as underflow or leach solids, which will be containing B in it and some amount of solution A plus C, because you are not able, it is not feasible to have perfect separation where you are separating all A plus C from the solid phase. So since this perfect separation is not possible, there will be little quantity of solution, that is A plus C, that will be there with the leach solids. So the underflow will be containing insoluble solids in it, plus some quantity of the clear solution. What is the clear solution? It is solution of C in A. So this combination of mixer and settler, it forms one stage. So in place of settler, you could have filtration, or you can have drainage. Provision for draining the clear solution. So this is one stage. This combination forms one stage in the stage-wise contact equipment. So let us move ahead. Now, as per requirement, multiple stages can be used. When you have multi-stage operation, either multi-stage cross current or multi-stage counter current, then depending on what is required, you can arrange those stages in that way. So as per requirement, multiple stages, they can be arranged in a desired cascade. What is a cascade? Cascade is nothing but it is an arrangement. Cascade of multiple stages is an arrangement where multiple stages are arranged so that an output from one stage is an input to the next stage. So if you have to show it by a simple schematic diagram, you can show it like this. So if this is stage 1 and this is stage 2, then when the output from stage number 1 is an input to stage number 2, then we can say that this is cascade of 2 stages. So cascade of multiple stages is nothing but an arrangement so that an output from one stage is an input to the next stage. Two commonly used cascades, as was the case with liquid extraction, here also two commonly used cascades are cross current cascade and counter current cascade. I have discussed about counter current cascade in my previous 2 videos. I am giving link to the entire playlist of my videos on leaching. You please watch those videos. So two commonly used cascades in leaching, for leaching. One is cross current cascade and the other one is counter current cascade. And when you carry out leaching in counter current cascade, you have multi-stage counter current leaching, where multiple stages are arranged in a counter current cascade. So leaching in counter current cascade is nothing but multi-stage counter current leaching. And in this case, what happens, what is done, feed is admitted in the first stage and solvent is admitted in the last stage. I will shortly show you the schematic diagram. But right now you just understand, feed is admitted in the first stage and the solvent is admitted in the last stage. And then overflow and underflow, they flow from one stage to the other in a counter current manner. So in this way you have counter current leaching operation. And in this case, the operation has to be carried out in a continuous manner. You cannot carry out this operation in a batch-wise manner. The operation has to be carried out in a continuous manner. So let us move ahead. Why you need to understand this. The operation has to be carried out in a continuous manner. What is the reason for that? If you do that, then steady state conditions will prevail and it will be easier for you to write material balances for this operation. Material balances, because we will be writing material balances under steady state conditions. Let us move ahead. Now let us talk about the counter current cascade. So in this case, the feed mixture, which is mixture of solids B and C and the solvent A, they are contacted in a counter current cascade. And I will show you a cascade that will contain n number of stages, capital N number of stages. So this is stage 1, this is stage 2, this is stage 3, and then from stage 3 there are many other stages, and the last stage in the cascade is nth stage, capital N stage. So the stages from third stage and the last stage, they are assumed to be lying in this region, in this space. Now feed is admitted to stage number 1. I will tell you what are the notations that we will be using in the discussion. So feed is admitted in the first stage, whereas solvent is admitted in the last stage. So since the solvent stream is coming from a stage that is next to stage, the n stage, so it is considered to be coming from an hypothetical stage, the next stage next to nth stage. So that stage is n plus 1 stage. And I'll tell you what are the notations. So this 2 streams then will flow in a counter current manner through the cascade. So this is the stream that is coming out of stage number 1, the underflow that is coming out of stage number 1, underflow coming out of stage number 2, underflow coming out of stage number 3, then underflow that is coming from n-1 stage, and now it is entering in the nth stage. And finally, you have underflow that is coming out of nth stage. Then you have overflow that is coming out of nth stage. Then prior to stage 3, you have stage 4, and this is the overflow that is coming out from stage 4. Then this is overflow that is coming out of stage 3, overflow that is coming out of stage 2, and overflow, finally, the final overflow that comes out of stage number 1. So final overflow in this case, in counter current cascade, it comes out of stage number 1, whereas the final underflow in this case, it comes out of nth stage. So I hope the schematic is clear to you. If you have any doubts, you please mention them in the comment section. Now let us talk about the notations that are used. Feed is described by F, capital F. What is capital F? This is mass flow rate of A plus C in the feed mixture. So we are not considering solids while defining F. Then YF is mass of C divided by mass of A plus C, which is nothing but weight fraction of C on a B free basis. And then you have NF, which is mass of B upon mass of A plus C, which is nothing but weight fraction of B on a B free basis. Then the solvent stream, solvent phase. So yes, N plus 1, this thing, it is nothing but mass flow rate of A plus C. Then X N plus 1 is mass of C upon mass of A plus C, which is weight fraction of C on a B free basis, and there will be no any solids. So we don't have any N for the solvent phase. Then you have overflows, various overflows, O1, O1, O2, O3, O4, On. So in this case, O1, O2, O3, On, these are mass flow rates of A plus C in those overflows. Then X1, X2, X3, Xn, these are masses of C per unit masses of A plus C. Mass of C divided by mass of A plus C in those overflows. That is, these are weight fractions of C on a B free basis. Then underflows, you have U1, U2, U3, U1, these are mass flow rates of all those underflows. And then Y1, Y2, Y3, each of this is mass of C divided by mass of A plus C in those underflow. And then you have N1, N2, N3, Nn. This is mass of B upon mass of A plus C in those underflows. That is weight fraction of B on a B free basis, weight fraction of C on a C free basis. Okay, now let us take the counter current cascade into our discussion, and I will draw an envelope that will cover the entire cascade. So you can see at this end, overflow from stage 1 is coming out of the envelope, whereas feed is entering into the envelope. And at this end, solvent is entering into the envelope, whereas underflow from N stage, it is getting out of the envelope. Okay, enough. So what happens when you have this envelope and when the feed mixture, that is B plus C and solvent, they enter the envelope, we are going to assume a hypothetical mixture to be forming in the envelope. So when the feed mixture and solvent enters the envelope, a hypothetical mixture is formed in the envelope. And for this mixture, let us denote the mixture. Let us use these notations. M is mass flow rate of A plus C in the mixture, whereas Ym is mass of C divided by mass of A plus C in the mixture, and Nm is mass of B upon mass of A plus C in the mixture. Ym is weight fraction of C on a B free basis, and Nm is weight fraction of B on a B free basis in the mixture. Okay, now we will write various material balances. First of all, we will write material balance for solid B. So the balance is mass of B, whatever mass of B is there in the system, it will be first in the feed. So mass of B in the system is equal to mass of B in the feed, that is equal to mass of B in the hypothetical mixture, that is equal to mass of B in the final underflow. And how do you write this? By with the help of a mathematical equation. So mass of B in the feed, you can get it by using these two quantities. Which are these two quantities? F into NF. So if you look at the definition of F, this is A plus C in the feed. And definition of NF is B upon A plus C in the feed. So A plus C gets cancelled if you take this product, and you are left with mass of B. That is mass of B in the feed. Now mass of B in the mixture, this can be expressed as a product of M and NF. Again, the same explanation applies over here. M is A plus C in the mixture, NM is B upon A plus C in the mixture. So A plus C gets cancelled, and you are left with B, mass of B in the mixture. Similarly, mass of B in the final underflow, this will be obtained if you take the product of UN into NN. So UN is A plus C and NN is B upon A plus C. So A plus C gets cancelled, and you are left with mass of B in the final underflow. So that's why the material balance for solid B, mathematically it will be written in this way. Let me first erase this so that we can continue the discussion. So mathematically it will be written as mass of B is equal to F into NF, that is equal to M into NM, that is equal to UN into NN. Let us call this as equation number 1. Now let us write material balance for solute C, and it will be given by this equation. F into YF plus, so this is solute in feed plus solute in solvent is equal to solute in mixture is equal to solute in the underflow plus solute in the overflow. F is A plus C. F is A plus C in the feed, YF is C upon A plus C in the feed. Similarly, Sn plus 1 is A plus C in the solvent, Xn plus 1 is C upon A plus C. In the mixture, M is A plus C in the mixture, Ym is C upon A plus C in the mixture. Underflow, A plus C in the underflow, C upon A plus C in the underflow. Overflow, A plus C in the overflow divided by A plus C in the overflow into C upon A plus C in the overflow. So in each case, A plus C gets cancelled, and you are left with C. So C in feed plus C in solvent is equal to C in the mixture, that is equal to C in the underflow. C in the feed plus C in the solvent is equal to C in the mixture, that is equal to C in the underflow plus C in the overflow. And I am calling it as equation number 2. So this is how you can write material balance for solute C. Now let us write material balance for the solution. Material balance for the solution, that is solution A plus C. So it will be written as F plus Sn plus 1 is equal to M, that is equal to Un plus O. That is A plus C in the feed plus A plus C in the solvent is equal to A plus C in the mixture, that is equal to A plus C in the underflow plus A plus C in the overflow. Simple material balance for the solution A plus C, and I am calling it as equation number 3. So in this way, we can write this 3 material balance equations for this counter current cascade that is containing n number of stages in it. Okay, so we have got those 3 equations. mass of B is equal to F into NF, that is equal to M into NM, that is equal to UN into NN. That was equation 1. Then F into YF plus SN plus 1 into XN plus 1, that is equal to M into YM, that is equal to UN into YN plus O1 into X1. That was equation 2. And then equation 3 is F plus SN plus 1, that is equal to M, that is equal to UN plus O1. And that was equation number 3. Now from equation 1, what I can write? Mass of B is equal to M into NM. So from equation 1, I can write a small equation. Mass of B is equal to M into NM. That is, NM is equal to mass of B upon M. After rearranging, I can write equation for NM. NM is equal to mass of B upon M. From equation 3, I can write F plus Sn plus 1 is equal to M. That is, now I can replace M in this equation for NM with this equation. So, using this in equation for NM, I get NM is equal to mass of B upon F plus Sn plus 1. So, I have done this in order to have an equation that can be used to calculate NM. Now, if you look at this equation, all quantities on the right hand side will be known to you at the start. And by using those quantity, mass of B will be known to you, F will be known to you, Sn plus 1 will be known to you. So by using the known quantities, you can find out NM. That will be required in our further calculations. Now from equation number 2, I can write this equation. F into YF plus Sn plus 1 into Xn plus 1, that is equal to M into Ym. I can write this equation from equation 2. So that is Ym is equal to F into Yf plus Sn plus 1 into Xn plus 1 divided by M. And in the next step, I can use this equation for replacing M. So that will give me Ym is equal to Fyf plus Sn plus 1 into Xn plus 1 divided by F plus Sn plus 1. Again, if you look at this equation, all the quantities on the right hand side of the equation, they will be known to you at the start, and then you can easily calculate the value of Yf, which will be required in further calculations. So at the end of this particular discussion, now we know how to find out NM and we know how to find out Yf. Let us move ahead. Okay, so we have those three equations. I'm taking them in my discussion once again. Now from equation number 3, you can write this. From equation 3, you can write F plus Sn plus 1 is equal to Un plus O1. And let me rearrange it. I will rearrange in this way. F minus O1. That is O1 I'm bringing to this side. So it will be F minus O1. That is equal to Un minus Sn plus 1. And let me call this difference as delta R. So in this case, delta R is called the difference point. I will shortly tell you the significance about this difference point. Now, what we will do, in order to show something regarding delta R, I will take the entire cascade into my discussion. But this time, I will consider only first 3 stages from the cascade. And then I will write material balance for the solution for first 3 stages. Let me show you those 3 stages. Now, these 3 stages are included in this green envelope. So, if you have to show it with the help of a block diagram, if the block is representing first 3 or if the block is containing first 3 stages, then one stream that enters this envelope is the feed stream. The other stream that enters this envelope, the green envelope, is the overflow that is coming from stage number 4. And then one stream that comes out of the cascade, out of this envelope, is the underflow that comes out from stage number 3. And the other one is overflow that is coming from stage number 1. Now, let us write material balance for solution A plus C for these 3 stages or for this rectangular block. So, this will be input is equal to output. Let me tell you all the material balances that we have written, or I have written, equation 1, 2, 3. These are all steady state material balances, because it is simply input is equal to output. We are not considering accumulation. So you just remember all the material balances that we are using or that we are writing in this case. These all material balances are steady state material balances. So steady state material balance for this block is F plus O4 is equal to U3 plus O1. Input is equal to output. And if you rearrange it, you can write it in this way. F minus O1 is equal to U3 minus O4. And F minus O1 over here it is delta R. That means this is also equal to delta R, and delta R is, as I said earlier, this is a difference point. And what is the significance of this difference point? Delta R gives the net flow of material towards the right. So you see F minus O1, that is this minus this. So this is giving net material flow towards the right of this plane. And if you look at the other terms, U3 minus U4, O4, U3 minus O4, again net flow of the material towards right. UN minus SN plus 1, UN minus SN plus 1. So this also gives you net material flow towards right. That is the significance of the point delta R, which is nothing but the difference point. Okay. Now let us follow these material balances on the equilibrium diagram. And the equilibrium diagram that we will be using is this one, where Nx and Ny, Nx is weight fraction of B on a B free basis in the overflow, Ny is weight fraction of B on B free basis in the underflow. So these N is defined, if you remember, this is defined as B upon A plus C. B upon A plus C, just a minute. So this is B upon A plus C. So in the overflow, it is Nx, but most of the time, almost all the time, there will be no solids in the overflow. In that case, Nx will be equal to 0. And if you are writing it for underflow, that is B upon A plus C, it will be N bar. So you are going to plot Nx versus X and Ny versus Y. And if you plot this, then you are going to get the equilibrium diagram. Let me first erase it. So you'll be getting a curve Nx versus X if there are values for Nx, that is the overflow contains solids. But mostly overflow will not contain solids. In that case, this curve will coincide with the x-axis. Almost all the time it will be true. That is this curve, there is no need of plotting this curve. This curve will be coinciding with the x-axis. And then when you plot Ny versus Y, you will be getting this curve. So in this case, what is done? Nx is plotted against X and Ny it is plotted against Y. So if there are values for Nx, then you will have this curve. And if the overflow is not containing any solids in it, that is all Nx are 0, in that case Nx versus X curve, it will coincide with the x-axis. But in order to have a complete discussion, I am showing this curve. But in actual applications, this curve will be coinciding with the x-axis, so you don't have to worry about it. So the first task is, in this case, is to locate point F. And this point F is located at YF and F. So YF will be known to you, NF will be known to you. You just have to locate first YF and then you have to locate NF, and the point with this coordinates will be nothing but point F. And then after that you have to locate Sn plus 1 Sn plus 1 will be located at xn plus 1, nn plus 1 on x versus nx versus x curve if it is there. If it is not there, which will happen when nx is 0, that is overflow does not contain any solids in it. So in that case, Sn plus 1 will be located on the x-axis. But let me show you how to locate it if there is a curve nx versus x. So it will be located at xn plus 1, nn plus 1. So with xn plus 1 known to you, you can locate it. So what you have to do, you have to first locate xn plus 1, then go to the curve nx versus x, and the intersection point will be nothing but this point, Sn plus 1. So after locating Sn plus 1, you have to connect f Sn plus 1 with a straight line. That is f and Sn plus 1, they are to be connected with a straight line. Then after that, we have to locate point un. All the information that is necessary for locating un will be either directly given to you or indirectly given to you. In any case, you can locate point un. And how to locate it? It is located at yn nn. But this time it will be located on ny versus y curve. So you just have to locate yn, go to the ny versus y curve, and the intersection point will be nothing but un, point un. So this is how you have to locate point u1. So at the end of this particular discussion, now you know how to locate point f, you know how to locate point Sn plus 1, and you know how to locate the point un. Let us move on. Okay, so after locating those 3 points, f, u1, un, Sn plus 1, you are locating, we have located f, then we have located Sn plus 1, we have, and then after that we had located un. Further, next task is we have to locate point m, and point m will be located on the line f Sn plus 1. So it will be located on the line f Sn plus 1. We have already drawn that line. So it will be located at ym nm on the line f Sn plus 1. Nm, first we will have to find it by using the equation. Nm is mass of B divided by f plus Sn plus 1, and ym is fyf plus Sn plus 1 into xn plus 1 divided by f plus Sn plus 1. So for finding both nm and ym, everything will be known to you. You just have to use these two equations and get the values of nm and ym. So either one of these two can be used. Let us learn how to use nm and locate point here. So you just have to locate nm over here, go to the line f Sn plus 1, wherever is the intersection, that will be point m. And if you look at the x coordinate of this point, that x coordinate will be nothing but y. So in this way, you can locate point m. Now we have to draw a straight line that starts from un and passes through m. So next task is we have to start at this point un, draw a straight line, allow it to pass through m, and then extend it to this nx versus x curve to get an intersection, and that intersection point is nothing but OM. So you will be drawing a straight line from un, allow it to pass through m, and then we will get an intersection on nx versus x curve, and that intersection point I will name that point as O1. Now look at these two lines. Yup, O1. I will be drawing a line that starts from yup, passes through O1, and then I will draw another line that starts at un, passes through Sn plus 1, And after drawing those two lines, I will extend them to get an intersection between those two lines. And that intersection point will be the difference point, that is delta r. So I will draw a line, straight line from F, allow it to pass through O1. I am drawing and I am then extending this line. Then I will draw a line that starts at UN, UN passes through Sn plus 1 and then allow it to extend to get this point. This intersection point is nothing but the difference point, that is delta. So this intersection point I am denoting by delta r. So let us move ahead. So with this structure ready, now we are ready to find the number of equilibrium stages. This structure will be useful for us to find the number of equilibrium stages. Now let us learn how to get how to find those equilibrium stages. So for that we will need the distribution diagram or XY plot, the other equilibrium diagram, where X is plotted on X axis, Y is plotted on Y axis, and you have the curve. So first thing is we have got O1. Now let us read the X coordinate of this point O1. So I am reading the X coordinate of this point O1 and I am naming that X value as X1. Now with this X1 known to me, I am going to the equilibrium XY diagram, locating that X1 on the X axis, and then I will find the corresponding value of Y that is in equilibrium with X1, and I will call it as Y1. So when I know this Y1, I will come back to this equilibrium diagram and locate Y1 on NY versus Y curve, NY versus Y curve. So I am locating this Y1 on the upper curve. So in that process I get Y1. Now I have 2 points, X1, Y1. So now since they are in equilibrium with each other, since we have got those two values from this equilibrium diagram, that is X1 is in equilibrium with Y1, they will be connected by a tie line. So I will draw a tie line that connects X1 and Y1. Now in the process after this, next is, now I will connect Y1. So now Y1 corresponds to the underflow that is coming out of stage number 1. Now it will be contacted with the solvent that is coming from, or the overflow that is coming from stage number 2. So for that I will connect Y1 with delta I by a straight line. I will draw a line from Y1 till I reach the point delta R. So in that process I get this point. I will read the X coordinate of this point, and that will be another value of X. Let me call it as X2. I will take this value of X2, come to the equilibrium diagram, locate X2 and get the value of Y that is in equilibrium with X2. I will take this value of Y2, locate it on the upper curve, that is NY versus Y curve. So this will give me Y2. Now X2 and Y2, they are in equilibrium with each other, so they will be connected with a tie line. So this green color tie line connects X2 with Y2. Now this Y2, it will be connected, we will have to draw a straight line from Y2 to delta R. So in that process I get this point. I will read the X coordinate of this point. I will call it as X3. Come back to the equilibrium diagram. Find out the value of Y that is in equilibrium with X3. Take this value of Y3. Locate it on NY versus Y curve. X3 and Y3, they are in equilibrium with each other. They will be connected by a tie line. Then I will connect Y3 with delta R. I will get this point. I will call it as X4. Take this value of X4, go to the equilibrium curve, find out the value of Y that is in equilibrium with X4. Take this value of Y4, and I will locate that on ny versus y curve. Now this time, when I'm locating y4, I'm crossing the point un. So once the point un is crossed, I will have to stop. So this will be the last location of y. It is y4, and x4 and y4, they will be in equilibrium with each other, so they will be connected with a tie line. So I have drawn tie lines till point un is reached, and once that point un is reached, my procedure stops. I will have to stop, and what is left, I will have to count the number of tie lines that I have drawn in the process. This is 1, this is 2, this is 3, and this is 4. So for this particular operation, 4 equilibrium stages are required to bring about the desired sector. So in this way, you have to find out the number of equilibrium stages in a typical multi-stage countercurrent leaching operation. You have to draw tie lines the way I have told you. You count the number of tie lines. The number of tie lines will be the number of equilibrium stages in this operation. So with this, I end my discussion for this particular topic. I have discussed multi-stage countercurrent leaching, how the operation is carried out, how to write material balance for insoluble solids, material balance for solute C, material balance for solution A plus C, then how to follow those material balances on NX, NY versus XY diagram, then how to find out equilibrium stages. So with this, I end my discussion for the theoretical aspects of multi-stage countercurrent leaching. In my next video, I will be solving one numerical that is based on today's topic. So let me end the discussion for this video. Thanks for watching the video. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. For now, have a nice day. Bye bye, and hope to see you soon in my next video. Thank you.